good morning if you're in US and stuff. But yeah, welcome to our another webinar from Compular on the topic of from language models to the lab, like a general framework of optimizing electrolyte formulations. So in this webinar, I'll kind of show you what we have been doing for last few months and about our new module, which is Formulation Optimizer, which is a And so I'm Harish Gudla. I'm CTO of Compular. I'll be I'll be giving you basic details of everything for the first 10 to 15 minutes, and then Simone will show you a live demo of how Formulation Optimizer works, what are the outputs it gives, and hopefully something new formulation if possible. Let's see. And yeah. Just before starting, I just want to inform everyone that the webinar has been recorded or will be recorded, and we'll share it soon in YouTube if you want to get back to it later. Yes, and please make sure that your mic is off so that you don't have any issues. Yes. So just a brief history of Compular. It's started by Rasmus, the CEO of Compular. He's also in the audience from his PhD project, or at least he developed a champion code for analyzing MD simulations for both battery electrolytes and polymer electrolytes. And then we started in 2021 or 2022. Sorry, 2020, and then got a pre-seed on 2022, and then 2023 is where our web application has been released, and from 2024 we have been live and surviving, developing multi-scale simulations and AI tools. So what we try to address at Compular is a traditional R&D process, especially in the field of liquid formulation, is quite slow. It takes years or decades to get a new materials to the market, and it takes very high cost when we try to screen through these thousands of formulations. There is a high chance of 95 to 99% being rejected because of not achieving the right R&D objectives, which is completely mostly done by lab. But in our solution is to set up a digital platform where we can simulate and test the new materials and formulations even before we start, and we get an idea of how we can reduce the R&D process. So yeah, right now we have a Compular Lab, our digital product, where we try to run simulations and AI to predict properties. So there are few modules that are already available to optimize liquid electrolytes using where we try to predict transport and structural properties from multidynamic simulations. We can also screen electrochemically stable electrolyte components and additives by using DFT calculations and predicting redox potentials. And we could also tune liquid formulation properties as a function of concentration and temperature. And there is also a cell level performance based module where you can have a custom battery chemistries and connecting from micro to macro scale simulations. And so this Compular Lab is a simple web interface where you can easily log in with your credentials, and then all the computing is done on cloud, where you don't have to worry about starting workflows and executing them. But it's a very simple user interface, which you'll see soon. So yeah, these are the modules that are available, and today I'll kind of go through the liquid formulation based modules on these three. Just give a how we came to the language, like using language models to optimize the formulations, just a backstory and our current module. So yeah, I'll just start with our basic electrolyte properties module, where you try to input a single composition in a plain language, or our chemistry language of like 1 molar LiPF6 in ACDC or something, and it will automatically fills in the form that requires to be that which requires to start the MD simulations, and it also sets all the simulation settings and what kind of properties you want to simulate. And you set up everything and you just click run, and it takes a few hours, 2 days to run the whole MD simulation and do the analysis, trajectory analysis, and calculate, get the main transport property results. In our case, battery. We are mostly build this for battery electrolytes. This is ionic conductivity, viscosity, transference numbers, solid diffusivity, and conductivity are quite well-known properties that needs to be optimized for a given electrolyte. And this, oops, okay, there should be some video playing about the molecule dynamic species. It gives out all the structural properties and everything at the molecular level insights. So yeah, so it takes for a single calculation, it requires one formulation at a given concentration and temperature. It gives deep insights, and it takes 1 to 2 days. But it is also a bit compute heavy. Even though we try to optimize all the processes, it takes compute for MD simulations to run, and we can run parallel compositions. Let's say it doesn't have to be 1C and 1T. You can run 10C and 10T, which still takes the same time, but the compute becomes 10 times then. But what if you want to predict the same kind of properties for a range of C and T, but you want it quite quickly, and such that you can estimate a range of concentrations where you can test. So to do that, I'll just quickly fix this. Should play it. Here. Okay, yeah, sorry. Now I found it. So this Formulation Explorer is our new AI tool that we built a few months ago, where it takes similar electrolyte composition, but instead of a single concentration and temperature, you can mention like a range of concentrations from 1 to 4 molar and temperature from 0 to 50 degrees Celsius. And it uses surrogate models to predict the whole properties. I'll just give a quick background there. Right now we have a ionic conductivity and viscosity properties, and we soon releasing solubility as a next step. So what happens under the hood is like we extracted lots of conductivity and viscosity data from various sources. From Sol is a very good lithium-ion battery electrolyte, and IL Thermo is a very common database for getting multi-solvent and very multi-salt ionic liquids. We can get temperature and property values as a function of them, and we also get the literature, which paper they have been referenced to. And we use our prediction model, where we try and embed or encode these molecules and the formulation in Kembeta. Kembeta, what is it? Ensemble, Kembeta training, and then network, and then it gives out the empirical model proper parameters. And so instead of predicting a single value, we try to predict functions of concentration and temperature, and it gives continuous functions. And for ionic conductivity, there are many models, and there is a one highly tested empirical model from Landsfield, where you can see a good function that tested and tried and follows the principle of the physical laws. But when we're looking for viscosity, there are many, but we want to see, but not, we cannot find empirical models every time we try to fit a new property. So we took a symbolic regression methodology, where it tries to search for a mathematical expression to fit the given data. So it does a few mutation and crossover permutations between different available mathematical functions, like multiplication, division, exponential factors, logarithm functions, and it tries to fit that given data. So we try to do that for the viscosity trained on a single nest database, where we have molecular fluids and a few 10,000 measurements, and try to predict a good function of as a function of concentration and temperature, and it fits quite well. And we tested that on the IL thermo data set. Yeah. And it works really well, even though it hasn't trained on the IL thermo chemistries and hasn't seen, but it still predicts in a really good range with a per surface RMSE. So, so we went with a symbolic regression, and then we trained our viscosity data extracted from both Calisol literature, and we're also extracting more literature data, so that it can get we can retrain the function more. Yeah, so now once we fit in all the symbolic model and also the initial input data, we get very clean results of as a function of concentration, and we can also change at different temperatures. We try to give a good error bar, which is predicted, which is averaged over different training test train splits between the data set within the data sets, just to give a good estimate. And we also show the data it has been trained on. The X's are the data which has been collected, and we also try to show these papers in our web app, so that you can click onto the link and see what exactly methodology they used and what kind of experimental conditions they used. Yeah, it's well and good for getting predictions for these things, but the webinar is for language models, and you're all here to see why we are doing that. So right now, this Explorer is quite good for one formulation. If you want to do hundreds, you can just create multiple ones, but it takes more time. So it is quick and reliable since it is trained on experimental data. It takes less than a minute, for example, to get those plots I showed, and it doesn't take much compute because these models are trained on small data point, like not a few thousand data points, and it's very simple to start. But you want to try thousands of formulations, and you cannot sit and write all the formulations by hand, right? So what we try to develop is, or like to have, is describe your own R&D objectives. Let's say maximize ionic conductivity and minimize viscosity in a very simple simple language that an electrochemist or experimentalist can understand and write, and then get thousands of formulations tried and tested on within a few minutes, and get a ranked list of all the compositions that you want to see. That's a really good idea, and how it will be very helpful for all the experimentalists to screen through these things properly. So that's exactly what we try to do with Formulation Optimizer, where we incorporate language models to extract, to understand the input formulation brief, or like the R&D objectives, and then try to get the formulation. So yeah, and so this is a brief overview of how it looks in the app. You'll soon see it. So it proposes. We give the initial prompt to LLMs, which is trained on our data, and then we give a plausible salt and solvent mixtures, and then the AI surrogates then uses the previously trained conductivity and viscosity models, and then it calculates those properties, and then it scores them according to your objective. Let's say you want to aim for high conductivity, so it tries to see which formulations have higher conductivity and also lower viscosity. And you can also give additional objectives like low cost. So you can set a certain limitations, how much cost you want to be. So this is a workflow, how it works. So you give the prompt, as I mentioned, this is the one I mentioned before, but you can also modify according to your temperature, what kind of preferences you need. And you generate input controls, where you can scroll through the sliders and say, like, you want a weighted objective of higher conductivity, but you don't worry about cost sensitivity. So you set the cost weights low. And you can play around accordingly to the operating temperature and other controls which are generated from the prompt. And then we use, it generates thousands of candidates. And then we use our surrogate models, which can also be retrained. So let's say you want to have a very specific application, we don't have the data yet, then we can scout through the literature or use your experimental data, and then we retrain it according for a better predictions, and then we can redo the candidate generations and then get it. So each candidate, as I mentioned, is encoded in Kembeta embedding, and it then fit into the predictive models. Then we do this optimization steps with multi-optimization steps based on the weights, and each optimization is on concentration here, but we can also do on the solvent compositions. So here it only optimizes for lithium salt concentration and then screens accordingly. Yeah, after that it gives you, we try to show top 100 compositions, but we can also screen differently. And here our main objectives are like conductivity, viscosity, and also we mentioned cost. So I haven't gone much brief here, but the cost we try to predict according to the individual component costs. And this is it's a rough estimate of this much dollars per liter. But then we use these three properties and rank them accordingly. Let's say, and then you get a list of various compositions at different salt concentrations, different solvent compositions, like you can see different ratios. In this case, we try to screen at minus 20 degrees Celsius. So, but that's an objective we try to screen for. Yeah, we also tried comparing different LLM models. We checked across GPT and Claude models, and we can clearly see that if you use a smaller or a low-cost model, it gives good compositions, but our aim is around roughly here, and you can see that just by having a better model, you can get more compositions in this range. So it's a yeah, you can either choose for high cost models and low performance, or low performance and high cost. So, but it can be changed accordingly. Yeah, I'll hand over to Simone just to show give brief live demo version of how this formulation optimizer works. Then you can go for the questions and yeah, question and answer session.
Yeah. So, can you hear me?
Yeah.
Okay. I will share my screen. And just for a double check, can you see my screen? I think so.
We can see, but it's a bit blurry.
Is it blurry?
Or it might take a minute to show
up. Can you see? Okay.
Yeah.
Can you see better? Can you hear me?
Yeah. Yeah.
I hope you can see better now. Anyway.
Yeah, now, yes.
We can.
So as Arish was saying, I'm going to present a bit the formulation optimizer. And okay, let me copy paste this. But basically, this is what is happening. So when you enter the Compular Lab app, there are several modules, and you can click Formulation Optimizer. You can create a job, and then you put the prompt. In this case, I'm choosing this prompt here. And then once you are pretty much satisfied with the prompt, you can generate controls. And here, as Arish was saying, you can tune those controls as much as you want. So if you want to give higher importance to conductivity, you can put it higher, and so on and so forth with the other properties. And here you can decide the amount of candidates that you want to generate. Here we are going to put 100 because of the time, but of course you can put whatever number. And just submit, you just submit optimization, and then you wait a bit for the candidate generation and then the candidate optimization. And in the meantime, I can show you what it will be the result. one possible result for this prompt with 1,000 candidates. So you can see that at the end of the optimization, there will be a property scatter and a candidate ranking, in which you can see like several scatter plots. In this case, it's conductivity, fluidity, but you can change one axis, actually both axes, to also include price, for instance. And you can see that each data point has a different color based on the salt. And yeah, in the bottom, you can see this candidate ranking, in which we use a score ranking to score like the candidates based on a combination of the objectives. So in this case, conductivity, viscosity, and cost. And we also provide an error bar because the models may be more prone to like maybe less robust with certain salts. So we also put here in this suggested formulation the entire like formulation, so from the best to the number 10, and then you can go on to see the top 100 in this case. So yeah, this is what is happening in for the formulation optimizer. Here it's finished. Okay, so for 100 is a little bit not interesting. It only generates LITF psi, unfortunately, but it's because it's very few amount of candidates. You can see that the formulation are actually different, but it only prefers to put LITF psi, which was one of the salts that we asked, actually. So another thing that Arish introduced was the Formulation Explorer. So I want to also quickly show you how the models that are called from the Formulation Optimizer are working. So you can see, for instance, in this example job here, it's loading. So 2 seconds. So you can express, either you can prefill with AI, or either you fill it by hand, and then you click Save and Predict, and it will predict conductivity and viscosity. And again, those are exactly the models that are used in the Formulation Optimizer. And here we have this experimental data threshold, in which you can see the data points that are used for training. And for each data point, you can also see the papers, the related papers, from where these data points come. So you can see that also in this case, we have some error bars. And those error bars, those like shaded lines, are the one that give rise to these error bars here. So yeah, here we have both conductivity and viscosity, as I said. And of course, this is a good case in the sense that we have data points in this case, but in some cases we don't have data points. So the Formulation Explorer is designed so that it will flag the case in which we are in out of distribution, like this one. And you can see that the error bars are very high, and the Formulation Explorer flag this, of course, both for conductivity and viscosity, of course. So yeah, with this, I think I finished. I mean, it was very quick introduction.
That's it. I'll just show the last slide, and then we can go to the questions.
Yeah.
Yeah, thanks for the demo, Simone. It's really good to see in live how it worked out, everything very nice. So our main idea is to just make it like a cloud code for formulations, where we describe the objectives, and this is the whole the initials. We build the initial optimizer, but we also can kind of we're working on literature agents and getting user lab data, and then incorporate them into the models and retrain them, so they can get better as long as we have to keep training and updating. Yeah, thanks you for listening for about our Formulation Optimizer module. I hope you have gain something, you can so you can use this QR code to sign up. You can see the demo version of the data, but you can try out the Formulation Explorer for free for like three predictions per day, but you can get more if you just contact us. Yeah, that's it from our side. Like, let's see if you guys have any questions. So you can just write it in the chat, or we can we can ask it if you can unmute and ask. Yes. So, okay. So we have one question from Agio. Have you observed AI hallucination during workflow optimization? If yes, how can it be avoided? So the hallucination here mostly we get from the formulation things. So if you can see, like in the optimizer, the example we tried to do, we asked for only lithium-ion batteries, but since our trained data also has NaPF6 and other sodium-ion based electrolytes, sometimes they just sneak peek into the into the list. So we are working on some kind of break or like hurdles or like conditions that it should follow right chemistries on both salt and solvents. And we try to, so this is the formulation brief is something that you can write, but there are also we give some previous tasks. We also set some rules and tasks so that it follows the liquid formulation kind of terminology and those kind of objectives. Yeah. Any other questions? Yeah. So we also trained the data on IL thermo, but we're still testing out its formulation optimizer part of it. So. If you want to try some kind of prompt that you want us to try, you can also share that in chats. We can try it and see and share you with the results. If you want. Yeah. We also I'll also share the sign up link here. Just that. And if you like to train this kind of models on your data, so these models can be very much detached from the what we have on the web. So on the web, we have a publicly trained model, but we can also have a very private models which are trained on in-house data or like in-house papers and stuff. Yeah, we'll share both slides and the recording soon after the presentation, after the webinar. Yeah, hope you liked our Formulation Optimizer and other tools, and our aim to get a full large language models incorporating into the material science and the formulation R&D more and more. Please contact us if you have some more ideas that we can incorporate or yeah, I'll be here for another minute